Welcome back to Fundamentals of AC Circuits. In this video, we're going to discuss power in RC and RL circuits. So the objectives for this video are that you will be able to calculate true, reactive, and apparent power that are dissipated in RC and RL circuits, and to illustrate the types of power dissipated using the power triangle. So we've already talked a little bit about power in RC and RL circuits. Just to recap, in RC circuits, when the resistance is larger than the capacitive reactance, more of the total energy is converted to heat by the resistor, which is power dissipation, than is stored by the capacitor. When the reactance is greater than the resistance, more of the total energy is stored and returned within the circuit than is converted to heat. Remember, there's no true power that is dissipated in a capacitor. So true power is what we use to describe the resistor. So true power is I squared times R, where I is the current running through the resistor. For power in a capacitor, we use reactive power, which is I squared times XC. So we have true power, which is the power dissipated in a resistor, reactive power, which we use for the power dissipated in a capacitor or an inductor. And then we have what's called the power triangle. So if I were to take the impedance for a resistor and a capacitor, I can draw an impedance triangle where the resistor and the capacitor form two legs of the right triangle, and the total impedance is the hypotenuse between the two. If I were to take that impedance triangle and replace that with power phasors, here's what it would look like. Power for a capacitor, I squared times XC. Power for the resistor, I squared times R. And then the total power for that total impedance would be I squared times Z. This is what we call apparent power, that hypotenuse for this triangle, apparent power. And apparent power is described in a few different forms. We could say I squared times Z, or total voltage times total current. That's your apparent power. So these three types of power form what we call the power triangle. So the horizontal leg is true power measured in watts. The vertical leg is reactive power measured in VARs, volt ampere reactive. And then we have the apparent power, which is the hypotenuse of the triangle, which is measured in volt amperes. That's the unit for apparent power, VA, volt amperes. That's your unit. So the power triangle is created by looking at the true power that's dissipated when you have a resistor, the reactive power that's dissipated when you have an inductor or a capacitor, and then what we call the apparent power, which is how we look at the circuit as a whole, as a combination of both true and reactive power. So we can use some trigonometry to manipulate the power triangle to find different values. For example, if I look at the triangle here, and this is my angle theta right here. This is my angle theta right here. I can say that the true power is the apparent power times the cosine of theta. And then apparent power is written as I squared times Z, so I can replace PA with I squared times Z times the cosine of theta. Or, since apparent power is also written as VI, I can say that the true power is VI times the cosine of theta. So once I draw the power triangle, I have a number of ways in which I can use it to analyze or solve for another value, depending on what I'm given and what I'm trying to find. So for a purely resistive circuit, or a purely resistive current, so a circuit with only a resistor, theta is 0 degrees. So your true power ends up being I times V. For a purely capacitive circuit, or a circuit with just a capacitor and no resistors, your theta will end up being 90 degrees, and you'll have no true power in your circuit. So the power factor is derived from the power triangle, and we take the cosine of theta, or theta is our angle in that power triangle, to determine what's called the power factor. The power factor is used to study power dissipation in a circuit. The smaller the power factor, the smaller the power dissipation. So the power factor can vary from 0 when you have a purely reactive circuit. That's when your resistance is 0. So when you have a purely reactive circuit, that means you only have an inductor or you only have a capacitor. And remember, there's no true power dissipated in an inductor or a capacitor. So it would make sense that your power factor is 0 because power factor is a way that we analyze power dissipation. If you don't have any resistance, you have no true power, you have no power factor. So your power factor can vary from 0 when you have a purely reactive circuit to 1 when you have a purely resistive circuit. So if you have no capacitors, no inductors, your power factor would be 1 because you have a purely resistive circuit where you only have true power, in which case you have power dissipation there. So this is the power factor, and it's used to study power dissipation in a circuit. We can build the power triangle in order to determine the power factor, but we can also calculate it manually by making circuit calculations. So you'll see that in an example. In an RC circuit, the power factor is a leading power factor because the current leads the voltage. So RC circuits, we have what's called a leading power factor. So what is the importance of power factor? Why do we look at it? Why do we use it? Here's a quick snapshot of the significance of your power factor. If you look at the circuit on the left, it says that a lower power factor means more total current for a given power dissipation. A larger source VA rating is required to deliver true power. So let's look at this. We have an AC source, and it's delivering 110 volts. The total current in this circuit is 0.24 amps, and we have a true power reading of 20 watts. And this is the load. So this could be some kind of system or circuit that is connected to our source here. This is our load, and the power factor is measured as 0.75. So this is a lower power factor compared to the circuit on the right. The power factor here is 0.95. And that just means that more total current for a given power dissipation. There's more current in the circuit to generate 20 watts here than there is here. The current level is higher here. More current is required to deliver the 20 watts of power that is measured here. When your power factor is higher, so the power factor in the circuit on the right is 0.95, the power factor is higher, I have less current used to deliver the same 20 watts of true power. So a smaller source can deliver the same true power in watts. A higher power factor means you have less total current for a given power dissipation. So this is one way that engineers will use power factor as they're designing a circuit. They'll use the power factor to determine the source they need to supply the correct amount of current to a load. The higher the power factor, the lower the current I need here, the smaller source I can use here. That's one reason that we study power factor. So let's start with our first example. For this circuit, we have a series RC circuit. We're going to determine the power factor, the true power, and then draw the power triangle. So first, let's start with the power factor. I need to find XC first. Remember, that's 1 divided by 2 pi FC. That gives me XC. Then I'm going to find ZT, 1 minus J, 3.39 kiloohms. Remember, R minus JXC. So plug in our values for R and XC, and we will get 3.53 kiloohms at an angle of negative 73.56 degrees. Now, power factor is equal to the cosine of theta, where theta is the phase angle of your total impedance. So our power factor is going to be cosine of negative 73.56 degrees, which is 0.283. Now remember, your power factor can lie anywhere between 0 and 1. And true power is what actually does the work in your circuit. The higher the power factor, the closer it is to 1, more work is being done in your circuit. Reactive power is just power that's stored and returned back to the circuit. It doesn't actually do any true work. So ideally, we want our power factor to be closer to 1. So looking at this power factor for this particular circuit, seeing that it's 0.283, if I desired a power factor that was higher, I may consider redesigning the circuit to use different components or perhaps a different frequency in order to increase that power factor so that it is closer to 1. Next, I'm going to calculate the total current in the circuit because I'm going to need that to find true power. So there's the total current. True power is I squared times R. Notice I'm not using any phasors here. We can just use magnitudes when we calculate power. There's your reactive power, I squared times xc. And then your apparent power, I squared times zt. Here's my power triangle, showing the true power on the horizontal axis, reactive power on the vertical axis, and then apparent power is the hypotenuse. We're also going to show theta, which was the phase angle of our impedance, at negative 73.56 degrees. Theta was negative, therefore your power triangle should be drawn with theta also being negative here, which means it should be drawn like in quadrant 4 if we're thinking about an XY plane. For an RC circuit, your power triangle should always be pointing down. So now let's talk about the significance of apparent power. Apparent power is the power that appears to be transferred between the source and its load. It consists of two components, your true power and your reactive power. In any electrical system, it is the true power that does the work. Reactive power is simply shuttled back and forth between the source and the load. So that means that in an ideal scenario, we want the power factor to be as close as possible in order for work to be done. So there may be times where you design a circuit, perform some calculations, and one of them may be power factor. If your power factor is too low, you may consider redesigning that circuit in order to increase the power factor to get it to be closer to 1. Here's another example where we're going to look at the significance of apparent power. Prove that the generator below is in danger of internal damage due to excess current when the load is changed from a purely resistive one to one that contains both resistance and capacitive reactance. So let's look at what we have. Here we have a circuit. We have a resistor connected to a source. The source has a rating, has a 5 amp maximum rating, 600 watt max, meaning that whatever you connect to the source should not generate more than 5 amps of current or 600 watts of true power. So with this particular resistor that's connected, it has a 24 ohm resistance. The power factor in the circuit is 1 because all we have is a resistor. We don't have anything else. And we can see the meters here measuring 5 amps of current and 600 watts. So right now it's at its limit. Can't go any higher, but it's at the limit. Everything is okay. Now let's say that I take the same circuit with the same source and I change the load so that it's not just a resistor, it's a resistor in series with a capacitor. Now the total impedance of this load is 18 ohms, and I've decreased the power factor from 1 down to 0.6. If I look at the meters, the meter for current is reading 6.7 amps. The current is too high. So you might have damage to your source because of excess current. But the watt meter says that the power went down. So how do I have two conflicting meters here? What caused this? And why do I need to be aware of this issue? So let's do a couple of calculations. If we look at image A, we know that power is I times V, so 5 amps times 120 volts, means you're going to have 600 watts of power. In image B, the voltage is going to be equal to the total current times the total impedance. So we know that current is voltage divided by impedance. So I have a 120 volt source divided by the impedance given as 18 ohms. That's how my current is 6.67 amps. The true power is what the watt meter is measuring. Remember, true power is measured in watts. And the true power being measured is your 6.67 amps squared times 18 times your cosine of theta. That's one of the formulas we discussed for true power. So when you do this calculation, your power comes out to be 480 watts. So your watt meter says you're not above the limit, but your current meter says you are. But this is only measuring true power in a circuit that has true power, reactive power, and apparent power. We're only looking at one piece of the puzzle here. So let's look at some other pieces. The apparent power in this circuit is going to be your voltage times your current, which is 800.4 volt amperes. Apparent power is what we should be looking at when we're looking at the readings for an RC circuit, if you take a watt meter and can connect it to an AC circuit with a capacitor or an inductor, and now you have the idea of reactive power that's introduced into your circuit, you can't just use a watt meter to understand what's going on anymore. Now we need to look at apparent power. And when you look at the rating for your source, you don't want to look at a rating that says 600 watts. You want to look for the rating that tells you what the apparent power maximum is. Because if you're only looking at the true power maximum and you're only measuring true power, you're going to measure with your watt meter something that doesn't necessarily indicate you have a safe circuit going on. So let's say that I'm only measuring true power, but my source starts to burn up. If I'm wondering what happened, it's because I was only measuring true power. If you look at the total current became too high because of the way the load was changed. With this circuit, with circuit A, the load provided 5 amps of current, which met the rating. With this load, I had too much current. But if you're only looking at true power and if you're only measuring with a watt meter, you're not getting the whole picture when it comes to an AC circuit where you have a capacitor or inductor included in your load. So apparent power is really a measure that we're going to be using when we look at the behavior of an AC circuit. We're not going to look at just true power when you look at an AC circuit. Let's look at one more circuit where we have a parallel RC circuit. We're basically going to determine the power triangle by finding the true, reactive, and apparent power. Let's start by finding XC. Then we're going to find the current through R using Ohm's law, voltage divided by resistance. Then we're going to use the current through R to find the true power. Remember, the true power is the current through R, not the total current in the circuit. Since this is a parallel circuit, we're not using the total current. We're using the current through R squared times R. And we can find IC using Ohm's law, and then find reactive power using the current through the capacitor. So we have two pieces of our power triangle. Now we need the third piece. Well, remember that the apparent power is the hypotenuse, the true power, and the reactive power are the two legs. So you can use Pythagorean theorem to find apparent power. That's one way you could do it. Next, I'm going to draw the power triangle. My true power is the horizontal axis, the reactive power is the vertical, and the apparent power is the hypotenuse. I know that this triangle has to point down because this is a parallel RC circuit. Then I can use some trigonometry to figure out what theta is. So I know the cosine of theta is adjacent over hypotenuse, for example, so I can use the inverse cosine of adjacent over hypotenuse in order to find theta. Just one of many ways. And then I could take the cosine of theta in order to find the power factor, which is 0.915, very close to 1. If we're looking at RL circuits, the power in an inductor is going to be determined by I squared times XL. We still have the true power dissipated by the resistor. And now notice that the orientation of the power triangle is shown with your reactive power pointing up instead of down. So for an inductive circuit, your power triangle is going to change and your vertical axis is going to point up instead of down. Other than that, everything we've used thus far will still apply to a circuit with an inductor. So look at the circuit on this screen and we see that we have a resistor in series with an inductor, and we're going to just draw the power triangle. So XL was given, but we're going to use that to find the total impedance of the circuit. Then we're going to find the total current in the circuit. We can see that the power factor is the cosine of theta, where theta is the phase angle of your total impedance. So our power factor is the cosine of 63.43 degrees, which is 0.447. Then we're going to calculate the true power, reactive power, and apparent power. Now that I have these three values, I can draw my power triangle. Remember, this time your reactive power is pointing up instead of pointing down. There's my apparent power and theta. So that's the power triangle if you have an RL circuit instead of an RC circuit. So as you see in some of the examples today, we've had power factors that were very different as we looked at different problems. Sometimes you may want to correct the power factor of your circuit. You can correct the power factor of an inductive load by adding a capacitor in parallel to your circuit. So let's say that you have a circuit that looks like this. R and L are in parallel here. Look at the current. And here's theta. This is what determines our power factor. I can add a capacitor in parallel to this branch, therefore reducing the angle of theta right here, this angle between the total current and the current through R. So when you add a capacitor, it reduces the phase angle and the total current, and that will increase your power factor. So oftentimes if you are in a design realm and you are building a circuit and realize that the power factor needs to be increased, power factor correction is what we call this, and this is one method of power factor correction where you can add a capacitor in parallel to your circuit in order to reduce the phase angle of the total current, therefore increasing your power factor. So that sums up our introduction to discussing the idea of power in an RL circuit or an RC circuit. This is as far as we're going to go with power in this class. It's sort of just an introduction, but as you go further, especially if you take a power systems or power electronics course, you probably will study this further, so you now have the basic ideas about power in an AC circuit. If you have any questions, please shoot me an email, and that is the end of this video.